In the previous tutorial, we wrote code to process MIDI events data and get a plugin to generate audio data. But we didn't do anything with the output from the plugin. What we'll do this time is to save the output in a WAV file. The WAV file format is a subset of Microsoft's RIFF specification for the storage of multimedia, most commonly, but not exclusively, sound and video. RIFF stands for Resource Interchange File Format. These files consist of so-called chunks and subchunks, and in a WAV file there are at least two subchunks, a format chunk and a data chunk. Unsurprisingly, the format chunk carries the identifier WAV, which is, of course, an audio format. There are various audio formats, but the one we will be targeting is the pulse code modulation or PCM format. For us, the important thing to note about the PCM format are as follows. The audio samples stored in the file are contained in integers. Those integers can be 1-byte integers or 2-byte integers, or even more. In my program, I decided to work with 2-byte integers, that is 16 bits. In addition, regardless of how many output channels the plugin has, I will be creating a stereo sound file with 2 channels. Now, in a 16-bit stereo PCM file, the data is stored in this format. As for the values, they can range from the largest positive value that can be stored in a 2-byte integer to the most negative value that can be stored in a 2-byte integer. Those values are asymmetrical. That is, if 0 is the midpoint, then the most negative value lies a little bit further from 0 than the most positive value. Since the discrepancy is negligible, we can just ignore the very last negative value. Moving on to the actual layout and contents of the WAV file, this table gives us all the information necessary to construct that file. On Windows, data is written in Little Endian format. Thankfully, all the big Endian stuff are literal strings, so they can be hard-coded. In my program, I created a class called riffwave, and in that class, there is this variable with the first 44 bytes of the file, basically those preceding the data bytes, and the big Endian values are hard-coded there. Ignore these two functions here. They do the conversion from Little Endian to Big Endian, or the other way around, but as it turns out, they are not needed. Let's see what else is in this class. Of interest are these 3 functions here. In Begin Wave Audio, the WAV file is opened, and the first 44 bytes I showed you earlier are written out to the file. And in Write Sample block is where the most interesting things are happening. Memory is reserved for one block of data, and why just one block will become apparent when we look at the code where the MIDI events data are processed by the plugin. And then the sample values are written to the memory space we just reserved. Just as each sample value is written, it is multiplied by the maximum value an integer can hold, which is, as we saw earlier, 32,767. You remember that sample values range from -1 to +1, so we are just magnifying those values with a constant to satisfy the requirements of the PCM audio format. At the end, all these data are written out to the file in one fell swoop. In EndWave Audio, before the file is closed, the size field, which is at the beginning of the file, is updated. Now let's revisit the playMidiTune method I wrote last week. If you haven't seen part 2 of this series of tutorials, well, this program segment was developed in there, so at this point you might want to pause and watch part 2 first. There are only a few lines of code we need to add to this method, otherwise it remains the same. Before processing commences, a rifwave object is created, and this beginWaveAudio method is called. Then further down in the loop, just after the plugin generated some output, that output is written to the wave file by calling the rifwave object's writeSampleBlock method. In other words, the sound data in the wave file is assembled bit by bit from block size chunks at each iteration of the loop. When I say block size, I mean block size number of frames, which is, in our case, 1024 bytes, because we are dealing with stereo data. After the end of the loop, when all MIDI data have been processed, the wave file is closed. And that's all there is to it. And now we can test this program and see what happens. Fingers crossed, everything will turn out alright. First, I'm going to test it with the very simple MIDI file I used last time. I've got the file locations hard-coded here. At this point, I'm not going to make this program interactive. So, here we go. So far, so good. The output here is the same as last week, and it was explained then, so there is no need to spend time with it. Here is the generated wave file, so let's play it. Splendid! Works just as expected. This MIDI test file is longer. It should be more interesting. I'm now going to recompile the program with that file as the input. Super! As you can see, the trace output is longer. And now I play it. Fantastic! I just want to do one more thing. Here is the compiled program, and I'm going to run it from the command line and pipe the trace output to a file. Done. Here is the file that was just created. So this text file now contains the execution trace with this longer MIDI input file. I'll make the source code and the files that were just created available, and I put a link to them in the description. Don't blindly copy my program though. Write your own, because that's how you learn. Use my program as pseudocode only, or to get ideas from. This time we played some quote-unquote music that was produced by the plugin and proved that the program, in particular the processing logic, worked well. But we are not there yet, because ideally the music should be playing in real time. And how to achieve that will be the subject of the next tutorial.